Hi everyone. Today we have Ajith Nair from City University, New York. We speak on modular forms by theta function. Ajith is a third year PhD student at City University, New York. He did his undergraduate from ISA Pune in 2017. So over to you, Ajith.
Okay. Thank you. Thank you so much to the organizers of the seminar and especially Devendra. Um, so I'm a third year PhD student uh, studying at CUNY, and my advisor is Gautam Chinta. He's at City College, and so I work in number theory and. Uh, yeah, I'm a beginner in the theory of modular forms and automorphic forms, and so I thought it's like I'm grateful to for this opportunity to give a talk in the seminar. So I have prepared a presentation on a very particular example of a modular form which is constructed via theta functions. Hi, Professor Kulkarni. Uh, so let me begin by explaining uh, the the brief outline of my talk. So we consider this. So my reference for this topic is Diamond Sherman's book on modular forms and section 4.11. This is called modular forms via theta functions, and the book on modular forms. The theme of the book is itself modularity, and in the preface of the textbook, they mention how you can consider this quadratic equation x square equal to d, and look at the solutions modulo p, and how this is related to modularity conjecture, and in more generally you can look at the elliptic curve equation and look at the solutions mod p and how the number of solutions arise as Fourier coefficients of a modular form, and that's basically outlined in the preface of the textbook. Now we are going to do uh, a slightly more general case than the quadratic case. So let me begin by describing what that is. So consider this cubic equation x cube equal to d, where d is a positive integer, which is cube free. And for each prime p, let AP of C, so this equation I'm calling it as C, let AP be defined as the number of solutions of C modulo P minus 1. Now it is known that this AP, this has a very explicit formula. So just as in the quadratic case, we can find out what the solutions of x square equal to d are modulo P. Just as that, we can also consider this in the cubic case, and we have the following. So AP is equal to 2 if P is congruent to 1 mod 3 and D is a non-zero cube mod P. AP is negative 1 if P is congruent to 1 mod 3 and D is not a cube modulo P. and AP is 0 if P is congruent to 2 mod 3 or P divides 3 times T. All right. Now these numbers AP are going to be the Fourier coefficients of a modular form that we are going to construct. So we will use Poisson summation and cubic reciprocity theorem to construct modular form theta chi with Fourier coefficients AP theta chi. So the prime pth coefficient of theta chi is going to be AP of C. And we are also going to see that these solution counts, which are AP, they are also the system of eigenvalues arising from theta chi, which means that the modular form that we are looking at, it's going to be a eigen form for the a simultaneous eigenform for the Hecke operators. Okay, so the idea is that we will use these two main ingredients in the construction, Poisson summation and cubic reciprocity. And this is a very particular case of a more general construction, which was done, I believe, by Hecke. And the point of this talk is to illustrate some of these ideas in the construction, like where does Poisson summation come up and where does cubic reciprocity come up. And yeah, so okay, so that was the basic setup. Now I will start the construction, and please feel free to stop at any point if you have any questions. So we let Ez be e to the 2 pi iz for any complex number z. We consider A to be this ring Z adjoined with mu3, where mu3 is the primitive cube root of unity. So this is a quadratic ring. It's the ring of integers in the field Q adjoint mu3, and we call alpha to be 1 I times square root of 3. So just some technicalities that some definitions that we would need. We denote B as 1 over alpha times A. Then A is a subset of B, is a subset of 1 over 3A. So 1 over 3A is like a fractional ideal in the field. Right. And B is also like a fractional ideal in the field. Okay. Then if we look at absolute value x squared, so if you have x, which is x1 plus x2 mu3, where x1, x3 are any real number, x1, x2 are any real numbers, then this is a complex number, and its absolute value squared is going to be x1 squared minus x1, x2 plus x2 squared. We also have that the absolute value x plus y squared is absolute value x squared plus trace of xy bar plus absolute value y squared, and trace of z is nothing but z plus z bar. Okay, now with these few definitions, we are going to construct a theta function. So we will first define a theta function, and then later we will show that these theta function have some transformation properties which will later be used to construct a modular form. So the modular form is constructed using the theta function, and the modularity of the theta function will give us the modular form, the modularity of the modular form. So for any positive integer n, and any u bar which is in the quotient group 1 over 3a.
Is Z bar just the complex conjugate?
Yes, yes. Z bar is the usual complex conjugate. Yes. Yeah. So if you have any positive integer n and an element in the representative in the quotient group 1 over 3a mod na. So 1 over 3a was here. So we consider the a was the ring Z adjoint mu3. Okay, so this Z adjoint mu3 will look like a plus b mu3, right? Where a and b are integers now. So, and then we consider this quotient group 1 over 3a mod na. And so this is again going to be isomorphic to, so A is isomorph as an abelian group, it is isomorphic to Z2. 1 over 3a is isomorphic to Z2. So this is going to be isomorphic to Z mod NZ squared as an abelian group. Then we define a theta function. So for any such n and u, we define a theta function. Theta u bar of tau n is we sum over the elements of A. So it's an infinite sum, e to the power n times absolute value of u over n plus small n squared tau, where tau is now in my upper half plane. So this is the theta function that we construct. And if you have, so yeah, like many times the theta function.
Third A by NA, is that a ring or just an abelian group?
1 over 3a mod na, right?
Is that a ring or just a group?
1 over 3a mod na will be
Just an abelian group.
yeah, I mean I'm interested in the group structure, but I guess it's also a ring, right?
So
yeah,
Z mod NZ square, that could be a ring also.
yes, yeah,
But you probably do not need that ring structure.
exactly, yeah, we don't need the ring structure for now. We just need the group structure. Yeah.
And what is this? What is this notation? En, etc.
So this is the e of z is e to the 2 pi I z. I'm just abbreviating it as exponential of z is e to the 2 pi I z. So most of the time we see theta function as defined as something like, I don't have the exact definition, but we say, so if you have some character chi, then we define it to be chi of n e to the negative pi n squared t, the sum over n equal to negative, maybe there is a 1/2. So yeah, so it's not immediately clear how this theta function is related to the theta function that is more classical, but I will later show why these two are the same, like similar. Why the theta function defined here is a generalization of the classical theta function. So we will see that later. So yeah, right now we will just define it as this. So and then this is an infinite series, and we want to say that this is a holomorphic function. On H. Right, so it's a holomorphic function of tau. Tau is in the upper half plane. Now the first lemma is to show that these the theta function that we have defined, it satisfies some modularity properties. So I'm just going to write these down. So theta u bar of tau plus 1n is e to the power absolute value u squared over n times theta u bar of tau comma n for u bar in B over NA. So originally u bar was from 1 over 3a mod NA, but 1 over 3a contains B. B is 1 over I square root 3a. So this is 1 over I square root 3a. So for u bar in B mod NA, we have this property. We also have theta u bar tau n is summation v bar b mod dna, v bar congruent to u bar theta v bar d tau dn. So this property is not exactly the modularity, but this is also a useful property. So we are scaling. So on this side we have d tau dn. So we are scaling the variables tau and n, and then we try to see how is that affecting the theta function. The third property is again the modularity property. So if we take negative 1 over tau comma n, then this is going to be negative I tau over n square root 3 summation w bar belonging to B mod NA.
What do you mean by modularity property?
Yeah, I think I need to explain that. So I'll just get to that.
Sound like a modular group of it.
Yeah. So I mean, when I say modularity property, I just mean that under the action of the modular group. So yeah, so if you take the 1101 acting on tau, then that is just tau plus 1, right? And then if you have 0, 1, negative 1, 0, and this is just going to be negative 1 over tau, I guess. Yeah. So I just want the how does the theta function behave under these actions of the modular group? Yeah, so it's not exactly invariant, but then yeah, how it transforms. So this is my first lemma. I'm not proving it, but I will just indicate. So the first two statements are not very hard to prove. They are just simple substitutions and some minute observations. The third one, so the third statement requires Poisson summation. So just to remind, the Poisson summation formula says that if you look at the summation f of n over integers n and summation f hat of n, then these two are the same for for a nice class of function. Let's say f is in the Schwartz class. So for such a function f, we have this Poisson summation formula, a very beautiful formula. And the point is that this Poisson summation formula somehow allows us to prove the following. So if we look at theta u bar of -1 over it, so tau is a complex number in the upper half plane. But if we just look at tau on the imaginary line, so that means tau is it, t is positive. Then for such a tau, we can, so do I have a v? So this is a v actually, because I have a v here. And sorry, this is also a v. Doesn't matter, but yeah. So for such a tau, we can show that by using Poisson summation, we get this. E to the negative trace of b w bar over n, theta w bar it. Right, so if I take tau equal to it, then so basically t, if you substitute instead of t, you substitute 1 over t, then how does the theta function change? So that is a result of that requires Poisson summation formula, and yeah. So it's also related to the fact that the Poisson, the Fourier transform of the Gaussian has a suitable property. So like, yeah, I can't recall something exactly, but something like if the Fourier transform of the Gaussian is going to be 1 over square root t, or yeah, something like that. So I'm not being precise here, but this allows us to sort of get the second this particular claim. Now here tau was only in the imaginary line, but then once you have this property on the imaginary line, then because of the uniqueness theorem, if two holomorphic functions, they agree on a dense subset, or or on a set which has a limit point, then they agree everywhere, right? So then this, once you have this agreement on the imaginary line, then you are done. You basically have -1 over tau comma n is negative I tau over n square root 3 e to the power negative trace of b W bar over n, theta W bar I tau is, what do I have? Just tau. So then, yeah, then we can conclude the third statement. So the crucial thing is that, so yeah, I should say then by maybe uniqueness theorem, uniqueness of holomorphic function. We get, right. So the crucial thing is Poisson summation, and then by applying the uniqueness theorem, we get the third statement. So the lemma, we see that how does the theta function transform under the modular group? Okay. Now, when we are talking about modular group,
The theta function, can you go back to the definition?
Sure, yeah. This is my definition.
It is defined, so that series converges only on upper half plane, is it so?
Right, yeah. Yeah, tau is taken to be in the upper half plane. Yeah.
Why not? I mean, where does it fail to converge in complex?
I don't know the answer to that. I mean, yeah, I mean, this is more like a standard thing to do. Like, yeah, we want to take an infinite series and we want to, right, yeah. But I don't know the answer to your question. But I mean, it is possible that it converges outside of the upper
Yeah,
half plane also.
No, I'm just trying to see one point where it diverges or something like that. But outside upper half plane.
Outside upper half plane. Yeah, I'm not so sure.
Okay.
I mean, I guess like if you put tau equal to 0, then it may not converge, right? Because you just get e to the, yeah, like,
1
yeah.
plus 1 plus 1 plus 1.
Yeah, it's just 1, right, for all n. So that won't converge. But
yeah, sure.
yeah.
Okay.
So
Alright.
yeah, usually we define this as an infinite series, and we try to say that it's a holomorphic function. I mean, I haven't explained why it's a holomorphic function. Yeah. Okay. Now, when we talk about modular forms, we also want to know what the congruent subgroup is under which the modular, for which the form is modular. So we consider this group first of all. So next, we show how the theta function transforms under the group gamma naught 3n comma n. So this is the group of matrices in SL2Z such that B is congruent to 0 mod n and C is congruent to 0 mod 3n. So C is divisible by 3n and B is divisible by n, and AD minus BC is 1. So then the proposition is that let n be a positive integer then theta u bar acted upon by gamma. Sorry. So I'll explain what that notation is. Of tau n is going to be the Legendre symbol D3, theta a u bar, tau a, tau n. where U bar is in A mod NA and gamma is equal to A, B, C, D, and it is inside gamma naught 3n comma n. So this action, this is this is the standard weight K operator in SL2Z. So if you take for gamma in SL2Z, and if you have a function in the upper half plane, then the weight K operator of gamma is basically you have this automorphy factor C tau plus D to the negative K F of tau Z. So, and then the modular form is basically something which is invariant under this weight K operator, because you want this to be equal to F, right? So that's what modular form means. So that's the modularity condition. So you define this F gamma K, and you can also define this more generally for gamma inside GL2Q plus. There we have to stick a determinant factor. So this is defined as determinant gamma to the K minus 1, C tau plus D, and the rest is as it is. So F of tau Z. Okay, so here we are looking at K equal to 1 and gamma is inside SL2Z.
Gamma 0, 3n comma n, that's a subgroup of finite index in the modular group.
Yes.
What is the index?
That I don't know actually. So I will show that you can conjugate this matrix to. So you can conjugate this this group by, what is it? So I will show that delta. So I will show that this is equal to delta. Sorry, this is equal to delta inverse gamma naught 3n squared delta. And gamma naught 3n squared is a congruent subgroup. So yeah. So I will show that this is true later. And
Delta? Delta.
Sorry?
Delta is what?
Delta is, delta I didn't tell you. Delta is N001.
Okay.
So I guess we are working in GL2Z. Or no, sorry, GL2Q plus, yeah. Right. Yeah, so this I'll need later. So the point is that it is easier to first show the transformation property for this subgroup gamma naught 3n comma n, and then we will conjugate it and then get the modularity property, the transformation property with respect to gamma naught 3n squared. And the gamma naught 3n squared is the congruent subgroup for which we will define the modular form. Okay, so and then we also see that we have this character, right? So we have this character, which is the Legendre symbol coming up. So yeah, that's why we have this modular form with respect associated with the character. So the point is that we have this kind of a transformation property. And now, so yeah, so let me just so now to construct modular form, we need to conjugate and then symmetrize. So I'll explain what that means, or at least the interpretation to construct modular form from theta function, right? So we had a theta function, and we will construct the modular form. So we take this delta n001, n001. Then, as I told you, that this gamma naught 3n squared is a conjugate of gamma naught 3n comma n. And so what we get is that the theta u bar acted upon by delta gamma tau is going to be theta u bar acted upon by gamma prime delta, where gamma prime is equal to delta gamma delta inverse is inside gamma naught 3n comma n. So my gamma is now inside. So for gamma equal to a, b, c, d inside gamma naught 3n squared. So if I have delta gamma, then that is same as gamma prime delta. And then by the previous proposition, this is going to be equal to the character d over 3 theta a u bar delta of tau. So we see that if you just take theta u bar delta, then so this is the same as theta u bar delta applied gamma 1. So that means that if you just consider this one, then this has a nice transformation property with respect to gamma naught 3n squared, where delta is this n001 matrix. So that's why we first conjugate by delta. And then what do I mean by symmetrizing? So, right, so by symmetrizing, what I mean is what I think they mean in the textbook is the following. So if let n be a positive integer, and this is the main theorem which shows that the modular, how is the modular form constructed. So if you have a character of the group A mod Na, the multiplicative group A mod Na, and you extend it multiplicatively to A. Multiplicatively to A, then define. So now I'm going to define what my modular form is. A chi of tau is going to be 1 over 6 u bar in A mod Na, chi of u theta u bar of n tau comma n. So we initially, when we defined the theta function, this was fixing a u bar, and now I'm I'm varying my U bar inside this finite group A mod NA, and I'm twisting these theta function by chi, and I'm summing over all of these twisted theta functions. And that I'm going to call it as my modular, and that is going to be the modular form theta chi. So that's what I mean when I meant symmetrizing. So we first conjugated the right. So theta U bar, yeah, and then so yeah. So this is yeah. Then the claim is that what the theorem says is that this is going to be a modular form. So if you act it by gamma, then you are going to get chi of d Legendre symbol d over 3 theta chi. Gamma is a b c d. It's in gamma naught 3n squared. So this is a modular form of level of weight 1 of level gamma 0 3n squared associated with the character psi, where psi is the character which is chi of d times the Legendre symbol d over 3. Because of, yeah, I mean that's because of how the transformation of theta chi is with respect to gamma naught 3n squared. So if I take the character psi to be chi of d times the Legendre symbol d over 3, and this psi is going to be a Dirichlet character for the mod 3n squared, right? So this is a Dirichlet character mod 3, and chi, remember that it was A mod NA is isomorphic to Z mod NZ squared. So this chi is a Dirichlet character mod n squared. So the product is going to be a Dirichlet character modulo 3n squared. Okay, and then that's the theorem that this modular form theta chi is going to be in the space. It's a level 1, sorry, a weight 1 gamma naught 3n squared level modular form with the character psi. Okay, so yeah. So so I don't think I will prove this theorem, but I will now point out how this theta function can be rewritten in terms of so that so that the expression looks more like the classical theta function. So the definition of the theta function was, I mean, it's already there. So U bar inside A mod NA, chi of U, theta U bar, and tau comma n. So if I expand the definition of the theta function, then this was summation n belongs to A, e to the power n times U over n plus small n squared n tau. And this, if you do some simplification, you will get this as summation n belongs to A, chi of n, e to the absolute value n squared tau. And then, yeah, now this should remind you of the classical version. So if I go back to the beginning, actually I erased the classic. Oh yeah, it's here. So this was the classical version of the theta function, chi of n e to the negative pi n t squared. And now here you can see that, so instead of summing over all integers, we are now summing over this ring, n belongs to A, of chi of n e to the power absolute value n squared tau. So this, yeah, this tells us that this is actually a generalization of the classical function, and this also allows you to get the Fourier coefficients. So if you take sum over all n for which absolute value n square is equal to m, of chi of n. So I'm replacing absolute value n squared by m. Then the Fourier coefficient you can see is going to be the bracket term. Therefore, the mth Fourier coefficient of theta chi is going to be 1/6 summation n belongs to A, absolute value of n squared equal to m, chi of n. So that is going to be the mth Fourier coefficient. So yeah, it is so what this summation looks like. So first of all, A is going to be, so let me just remind you that A was the ring Z adjoint mu3. So in the complex plane, so you have the complex, the unit circle, and let's say my 1 is somewhere here, mu3 is going to be here, mu3 squared will be the conjugate. And then if you look at the translates of this, what you're going to get, it's a triangular lattice. Yeah, so I don't know the exact picture, but might be something like this. So the vertices are going to be these lattices, and you can extend this. So these are going to be the darkened points are my elements of A. And I'm looking at the elements of A whose length, whose distance from square of distance from the origin is equal to m. And I am summing over the value of chi of n over these elements. Okay. Yeah. So now, so this was the hard part of the construction. I mean, the construction is using the Poisson summation formula. The next part, so just to remind you, the what we are trying to do here is that the modular form theta chi, the Fourier coefficients, the prime Fourier coefficients are going to be equal to the solution counts of the equation that we had before. So the AP of C was this. So the solution counts of this equation are going to be the Fourier coefficients of my modular form. So to show the final thing, I need to explain cubic reciprocity theorem. So the other ingredient is cubic reciprocity theorem. So to describe that, we first look at the unit group of A.
Is that Euler
Plus or minus 1 plus or minus mu3
reciprocity?
plus or minus mu3 squared.
Euler.
Okay.
Now,
Quadratic cos.
if chi is non-trivial on A star, then
Euler can be proved.
summation
Euler's work.
of chi of n is going to be 0 on A star. And this will imply that the mth Fourier coefficient is 0 for all n. And so theta chi will be 0. So that means that we should not have, we should have chi to be trivial on A star. So the point is that, but now we showed the theorem is true for any character chi. We are going to now choose a particular character chi for which the modular form theta chi will be the required modular form that we want, whose Fourier coefficients are the correct Fourier coefficients. And so that that appropriate Dirichlet character that we want, that is given to us by cubic reciprocity. So a weak form of cubic reciprocity states that so then there is the statement. So let D belongs to positive integer, B cube free. N is the product of 3 times product over the prime divisors of D. Then there exists a character chi from A mod NA cross to 1 mu 3 squared, such that the multiplicative extension of chi to all of A is trivial on A star and on primes P not dividing N, while on elements of A such that, so this, yeah, I'm not sure if I'll be explaining it in detail, but we'll just take it for granted that we have such a character chi which satisfies these conditions. And this is the what cubic reciprocity tells us. So there is a particular Dirichlet character associated to A mod NA cross. Again, this is isomorphic to Z mod NZ cross Z mod NZ multiplicative group. And so this is a Dirichlet character modulo n squared. For this character, chi, theta chi, which we constructed, is going to be a modular form of weight 1 level gamma naught 3n squared associated with psi where psi is the quadratic character with conductor 3. So psi was defined as you take this character chi and then multiply by the Legendre symbol. So the conductor of this psi will be 3. Psi is not going to be primitive because it's this is modulo 3n squared. So psi is mod 3n squared. And then finally, we get what we want. We see that, so this will require, so we already computed what the Fourier coefficient looks like. And then from 1, we see that AP of theta chi is going to be equal to AP of C, which I wrote down in the beginning. And yeah, so this particular chi, which comes from cubic reciprocity, is going to give us the correct Fourier coefficients. And then lastly, how is this
So
related
such
to
chi is
modularity?
unique, is it?
Sorry?
Such chi is unique. Okay.
Such, yeah. So in the statement that I saw, there is no uniqueness. But I guess maybe implicitly we are saying that it is with these conditions, the character is unique.
Okay.
But yeah.
Okay. Good.
Sometimes it feels, or maybe, yeah, since we are not really saying that there is such a unique character, like we just want the existence of one such character for which we want it is true. So yeah, maybe, yeah, I mean, it's a different question whether there is another character for which we get the same Fourier coefficients, but yeah, I don't
I mean,
know.
it has to be, I think, because I mean, if two modular forms have same Fourier coefficients, then they are same.
Yeah, but these are only prime Fourier coefficient. Yeah, I think for all Fourier coefficients, if they are equal, then yeah, then by the
No,
uniqueness.
even
Right, because of the maybe the multiplicative property of the Fourier coefficients. Yeah, I guess that might be true. Yeah. Is that what you were trying to say?
yeah, I mean, having equality for prime Fourier coefficients is enough.
Right. Yeah. I didn't think of that. Yeah. Yeah, you're probably right.
Because you said that it is eigenform, right?
Yes.
In the beginning, you said it's eigenform.
Yes. Theta chi is actually, yeah. So that's what I was going to say in the next line. So theta chi is a normalized eigenform, which means that it is simultaneous eigenfunction for the Hecke operators. Also, the modularity is because this is not proved in the same section, but later they have, when they talk about Galois representations, they have mentioned how this modular form arises from a Galois representation, or rather I guess it runs both ways. So this part of the theory I'm not familiar with, but for the sake of completeness, I will just say that there exists a Galois representation associated to theta chi. So how do you get this? So you embed S3 inside GL2Z. Then if you consider Q adjoint cube root of D mu3, then we get a Galois representation of F in GL2Z. And when T does not divide 3D, the trace of this representation on the Frobenius element, Frobenius prime P, is going to be AP. So this part I'm not, I don't know, but yeah, I thought that I will mention this so that we can see how the modular form and the Galois representation, what is on the side of Galois representation. And this is the, this is the correct Galois representation associated to theta chi. Okay, so that's also, so the point is that this is a very particular example of a more general construction of modular forms via theta functions. And hopefully I have tried to convey some ideas that are relevant when we do this kind of a construction in the theory of modular forms. Okay, thank you.
Thanks.
Yeah, if you have any questions, I can answer. I'll try my best to answer.
This cubic reciprocity is due to Eisenstein, right?
I don't know, but yeah, when I was reading this cubic reciprocity, no. So Gauss also has Gauss actually stated a cubic reciprocity theorem. Maybe the complete version was done by Eisenstein, but when I looked at Wikipedia, there is a version which is attributed to Gauss.
I think Eisenstein also did something. And
yeah, so interesting. Yeah,
due to Euler about this ring of integers.
Yes. So this ring of integers is called Eisenstein integers, like the Z adjoint mu3 is called Eisenstein integers. Sometimes Euler integers also. So maybe Eisenstein has done cubic reciprocity. Yeah.
And now if your 3 is replaced by general prime cube, that is the original Artin reciprocity, right?
Yeah, I don't know about that, but yeah, I've heard these. I'm still like trying to get there. So maybe if Mihir knows, he can.
So if there may be similar interpretation for all these AK eigenforms.
Right.
In general, some number theoretic interpretation for the AK eigenforms, which are the common.
Right. Some related to some reciprocity in number theory. Right. That might be a good question to think about. Like how does this generalize when 3 is replaced by some other prime?
They may be class number, maybe coming.
I think. I think I don't know, but I haven't read this part from Diamond Shulman. But if you start with the equation, whose Galois group is abelian, then I guess this works, right? This
Yeah.
should be the generalization, right?
Okay, okay.
No, I'm asking people. I also don't know.
So
Like, do they
what
comment
is
upon how which type of equations give rise to modular forms in this section?
not in this section? So in the preface, they start with the quadratic case, x square equal to d.
Mm.
That is the more elementary case, and there uh, that's the more elementary version of modularity. Then they mention how if you take the equation for the elliptic curve, then you actually see the modular forms.
No, but
And then
elliptic curves, you have equation in two variables. Here you are
yes,
only considering one variable.
one variable. Yeah, yeah. So in this section, they talk about the cubic equation. Perhaps they also talk about other equations, but I haven't seen those. Yeah, but yeah, if I read more about this, I'll let you know.
Yeah, okay. I will also have a look at this. 4 point, which section? 4.
This is 4.11.
Okay.
Yeah, modular forms by theta functions.
Thanks, Ajit. It was very nice presentation actually.
Okay, thank you so much. Yeah, I mean, I try to convey some ideas, but
No,
yeah,
it was
so
good actually. Connecting the theta functions and modular forms with the
yeah.
representation
Yeah,
finally.
this section is also very nice. Like there are a lot of computations, but the ideas are very interesting.
Okay. See you sometime.
Okay, thank you so much. Thank you once again for this opportunity.